Hello and welcome. Today, we're going to dive into a really cool statistical tool that helps us answer a question we see all the time. When you notice a difference between two groups, is that difference real or is it just random chance? Let's get ready to unlock the secrets of the independent samples t-test.
So let's imagine you're a researcher for a minute. You've come up with a brand new 10-week diet plan. Awesome. But you need to know, does it work the same for everyone? And more specifically, does this new diet work differently for men than it does for women? This isn't just some textbook question, right? This is a real-world problem, and statistics can give us a solid answer.
Now, to get a trustworthy answer, we can't just eyeball the numbers and make a guess. We need the right tool for the job. And when you're comparing the average results of two totally separate independent groups, like our men and women, that perfect tool is the independent samples t-test.
So what is this thing exactly? Well, it's a statistical test built for one key job: to compare the average score, what we call the mean, from two completely separate groups. It's the test that tells us if the difference we're seeing is actually meaningful, or if it's something that could have just happened by pure luck.
Okay, don't let any formulas scare you off. At its heart, the t-test is actually pretty simple. It boils everything down to a single number, a t-score. And you can think of it like a signal-to-noise ratio. The signal is just the difference you see between the two group averages. The noise is all the natural variation that happens inside each group. So a big t-score means you've got a really strong signal, a big difference that's loud and clear above all that background noise.
But hang on, before we can use this awesome tool, we got to make sure our data is playing by the rules. It's kind of like a pilot doing a pre-flight check. We have to check a few key assumptions to make sure our final results are going to be valid.
And there are three main rules on our checklist. First up, group independence. This one's easy. A person is either in the male group or the female group. They can't be in both. Simple. Second is normality. This just means that for both groups, the data on weight loss should kind of look like that classic bell curve. And third, homogeneity of variance. I know, it's a mouthful, but it's just a fancy way of saying that the data in both groups should be spread out in a similar way.
And this shows you exactly what that last rule means. See the picture on the left? One group is all bunched up and the other is really spread out. That's unequal variance. What we're hoping to see is the picture on the right, where both groups have a pretty similar amount of spread. That tells us we're comparing apples to apples.
All right, our pre-flight check is done. Everything looks good. Now we get to the exciting part. Let's crunch the numbers from our diet study and see what they actually tell us.
So the first peek at our results is right here. And just on the surface, it looks like there's a pretty big difference, right? We had 42 females in the study, and on average, they lost about 6.9 kilograms. The 45 males, on the other hand, lost an average of 3.7 kilograms. Wow, that's a difference of more than 3 kilos. And when you plot it out like this, that difference really jumps out at you. You can clearly see the average for females is way higher than for males. But this brings us to the million-dollar question for every researcher. Is this difference actually big enough to count? Is it statistically significant, or could this have just happened by dumb luck?
Now, before we answer that, we have to double-check that we were cleared for takeoff. Remember those assumptions? Well, we ran a couple of specific tests to check them. The Shapiro-Wilk test told us our data was normal, and Levine's test confirmed our variances were equal. Now, here's the tricky part. For these specific tests, a not significant result is great news. It's what we want to see. It means our data played by the rules, and we can go ahead with our t-test.
And here it is. This is the moment of truth. This table has our answer. Now, there are a few numbers here, but the one I want you to focus on, the star of the show, is in that column labeled P. That's our p-value, and it's going to tell us everything. And our p-value is less than 0.001. Let that sink in. That is a very, very small number. It basically means that there's less than a 1 in 1,000 chance that we would see a difference this big just by random luck. So, with a p-value that incredibly tiny, we are officially ready to make our call. It's time to state the final verdict and answer that question we started with. Because that p-value is so much smaller than our standard cutoff, which is usually 0.05, we can say with a lot of confidence that the difference we saw is statistically significant. It's not a fluke. The answer is yes. Based on our data, this diet really did work differently for the men and women in our study. Now, for any of you students watching this, take a good look. This is pretty much the perfect way to write up this kind of finding in a paper or a lab report. See how it's short, sweet, and to the point? It has all the key info, the t-value, the degrees of freedom, and of course, that all-important p-value.
It also mentions something called Cohen's d, which tells us how big the difference is. And in our case, it was a large effect.
Okay, but what happens if your data doesn't pass that pre-flight check? What if you run the tests and you find out your assumptions were violated? Do you just throw your hands up and give up? No way. Statistics always has a plan B.
If your data isn't shaped like a nice bell curve, or maybe you're working with data that's ranked, you just switch over to the t-test cousin, the Mann-Whitney U-test. As you can see here, instead of comparing the average or the mean, this test compares the median, which is just the middle value of each group. It's the perfect backup plan to have in your pocket.
Here's a quick example. Let's say you were comparing pain scores, rated from 0 to 10, for 2 different treatments. That kind of ranked data is the perfect time to use the Mann-Whitney U. And when you go to make a graph, instead of showing the means, you use these things called box plots, which are great for showing the distribution and the median.
So there you have it. Whether you're comparing weight loss or pain scores, you now have a powerful framework for figuring out if 2 groups are truly different. You've learned how to pick the right tool, check the data, and read the results to find the real story hiding in the numbers. The only question left is, what hidden story are you going to uncover next?